What if I told you that everything we can see, every star, every galaxy, every shimmering speck of light in the night sky, is just a fraction of the universe's true story? The rest is hidden in plain sight, an invisible force so mysterious it defies our most advanced tools and brightest minds. This is dark matter, the cosmic phantom that shapes the universe yet remains utterly elusive. It doesn't absorb light, reflect it, or emit a single detectable signal, and yet without it, the galaxies we know wouldn't exist. They'd fly apart, their stars scattering into the void like sand caught in a cosmic wind. But dark matter holds them together, weaving an unseen scaffold across the cosmos, a hidden architecture that cradles galaxies in vast, shadowy halos. These halos are more than just cosmic glue, they're the universe's best-kept secrets. Imagine a spider's web, its delicate threads invisible until the morning dew catches them. Dark matter halos are like that, unseen, but their presence is written in the way galaxies spin too fast to hold themselves together, in the way light bends around empty patches of space as if something massive lurks there. Scientists estimate that dark matter outnumbers the ordinary stuff, the atoms that make up you, me, and every star by 5 to 1. That means most of the universe isn't just unknown, it's fundamentally unknowable with today's tools. And yet, we've pieced together clues, chasing shadows across the cosmos to unravel 25 of its most haunting mysteries. That's where our journey begins. Together, we'll venture into the depths of these enigmatic halos, where the rules of physics twist and the very fabric of reality feels up for debate. We'll explore why some galaxies orbit in impossible formations, how dark matter might hide entire parallel universes, and whether it's even matter at all or something far stranger. This isn't just a tour of cosmic oddities, it's a detective story on the grandest scale where every clue leads to deeper questions. By the end, you'll see the night sky differently, not as a static painting, but as a living, breathing mystery, its darkest corners whispering secrets we're only beginning to hear. So, are you ready to step into the shadows? The first and most baffling mystery of dark matter is this: how can something so massive, so essential to the universe's structure, remain utterly invisible to us? It's like standing in a room where every object casts a shadow, but you can't see a single thing creating them. Dark matter doesn't just avoid the spotlight, it ignores light entirely. Unlike stars, planets, or even the dust between them, it doesn't absorb, reflect, or emit a single photon. If our eyes could perceive only gravitational effects, we'd see the cosmos brimming with dark matter's fingerprints, galaxies spinning faster than they should, clusters of stars held together by something unseen, even the very fabric of space-time bending around cosmic emptiness. This wasn't always obvious. Back in the 1930s, a sharp-eyed astronomer named Fritz Zwicky noticed something bizarre about the Coma Cluster, a group of galaxies millions of light-years away. The galaxies were moving so fast that, by all known laws, they should have flung themselves apart long ago. Zwicky called it missing mass, the gravitational glue that wasn't there, at least not visibly. His peers dismissed it at the time, but decades later, another astronomer, Vera Rubin, found the same strangeness in spiral galaxies. Their outer stars whirled around the center at speeds that defied explanation, as if hidden hands were tugging at them from the dark. Today, we've traded Zwicky's pencil and paper calculations for cosmic detectives like gravitational lensing, nature's own magnifying glass. When light from distant galaxies warps around what looks like empty space, it reveals the presence of vast dark matter halos, bending space-time like a marble resting on a stretched sheet. Even with these clues, the question remains, what is it? The leading theories range from exotic particles that barely interact with ordinary matter to primordial black holes forged in the universe's first moments. Some even suggest dark matter isn't matter at all, but a flaw in our understanding of gravity itself. one thing's certain: without this invisible giant, our universe would look nothing like it does. Galaxies would never have clumped together in the early cosmos. Stars would drift alone in the void. Dark matter isn't just a cosmic afterthought, it's the architect, the silent builder of everything we see. And yet, after nearly a century of searching, it still slips through our fingers like smoke, leaving behind only the faintest traces of its existence. But if dark matter is truly the universe's hidden scaffolding, holding galaxies together in vast, invisible halos, why doesn't the math add up when we look closer? Here's the puzzle: supercomputer simulations, based on our best understanding of dark matter, predict that the Milky Way should be surrounded by hundreds of tiny dwarf galaxy satellites caught in its gravitational grip. Yet when astronomers count them, they find barely a few dozen. It's as if someone erased 3/4 of the cosmic neighborhood overnight, leaving behind only ghostly traces. This glaring mismatch is called the missing satellite problem, and it's one of dark matter's most persistent headaches. The simulations aren't wild guesses, they're meticulous recreations of how dark matter should clump together under gravity's pull. Picture dropping ink into water. It swirls, branches, and forms intricate filaments. Dark matter behaves similarly, condensing into a cosmic web where strands intersect, creating dense pockets where galaxies form. Smaller clumps, those dwarf galaxies, should linger like crumbs around larger structures, but reality stubbornly refuses to cooperate. Either our simulations are wrong, or something's hiding these galaxies from us. One explanation whispers of warm dark matter, a lighter, faster-moving cousin to the sluggish, cold dark matter we usually assume. If dark matter particles were less massive, they'd zip around too quickly to form as many small clumps, neatly trimming the number of expected dwarf galaxies. Others argue the satellites are there just too faint to spot. Imagine trying to count fireflies from a speeding car. Some flicker so weakly they blend into the night. Recent sky surveys have indeed uncovered ultra-faint dwarfs, barely detectable against the Milky Way's glare, but even these discoveries barely dent the discrepancy. Then there's the darker possibility. What if dark matter isn't just hiding these galaxies, but destroying them? Some models suggest the halos around dwarfs could be so dense that their gravity crushes star formation, leaving behind barren husks. Or perhaps the Milky Way's tidal forces shred them over time, scattering their stars into ghostly streams. Every potential answer raises new riddles, a reminder that even our best theories are just sketches of a reality far stranger than we've dared to dream. The too big to fail paradox might sound like a financial crisis, but it's actually one of dark matter's most confounding cosmic puzzles. Picture this: supercomputer simulations predict that the darkest corners of our universe should be littered with massive, dense clumps of dark matter halos so gravitationally powerful they'd naturally birth bright, bustling dwarf galaxies. Yet when astronomers peer into the real cosmos, these heavyweight halos seem suspiciously empty. It's as if the universe forgot to build the galaxies these dark matter palaces were meant to house. This paradox gets its name from an eerie resemblance to banks deemed too big to fail. Just as those financial giants were expected to dominate, simulated dark matter halos are too massive and stable to not form galaxies. But reality begs to differ. Take the Milky Way's neighborhood. We've spotted a handful of dim, wispy dwarf galaxies orbiting us, but none match the sheer scale or brilliance the simulations insist should exist. The math says these dark matter giants must be out there, so where are their galactic counterparts? The answer might lie in something far more explosive than dark matter itself: supernova. Imagine a fledgling dwarf galaxy, its first generation of stars flickering to life. These stars don't die quietly. When the most massive ones explode, they unleash shockwaves fierce enough to blast away surrounding gas, the raw material for future stars. Without enough gas, star formation grinds to a halt, leaving behind a dark matter halo with no galactic sparkle. It's like building a stadium for a sports team that never shows up. But supernova might not be the only culprits. Some theorists argue that ultraviolet radiation from the universe's earliest stars could have sterilized these halos even earlier, ionizing gas before it could collapse into stars. Others suggest dark matter's own quirks, like its ability to interact weakly with itself, might redistribute energy in ways that prevent galaxy formation. The stakes are higher than they seem. If supernova or radiation truly are the missing pieces, it means dark matter's story is inextricably tangled with the ordinary matter we can see. The cosmos isn't a stage where dark matter dictates the script alone. It's a collaborative performance where stars, explosions, and even light itself rewrite the rules. Every failed halo is a reminder that the universe thrives on chaos, and that our models, no matter how sophisticated, are still playing catch-up. Dark matter halos should be cosmic fortresses, impenetrable, dense, and sharply concentrated at their cores, at least according to our most trusted simulations. But when astronomers peer into actual galaxies, they find something unsettling. The centers of these halos aren't cuspy and dense at all. Instead, they're fluffy, like a cloud dispersing at its heart rather than a mountain peaking at its summit. This mismatch, known as the core cusp problem, throws another wrench into our understanding of dark matter's behavior, forcing us to ask, is the universe tricking us, or are we missing something fundamental? Take the dwarf galaxy Fornax, for example. Its stars drift lazily around the center, their movements suggesting a gravitational pull far weaker than simulations predict. If dark matter were as densely packed as expected, those stars should be whipping around like frantic bees. Instead, they meander, hinting at a diffuse core where gravity's grip softens unexpectedly. This isn't an isolated case. Galaxies big and small, from spirals like the Milky Way to the tiniest dwarfs, show the same puzzling trend. So what's smoothing out these cores? One leading theory points to an unlikely culprit: stars themselves. When massive stars are born, they don't just shine, they fight back. Supernova explosions blast gas outward, creating waves of pressure that push against dark matter's gravitational pull. Over billions of years, this cosmic tug-of-war could stir the halo's center, churning it into a smoother, fluffier state. Imagine shaking a snow globe vigorously. The once settled flakes now swirl in a loose, even haze. But not all galaxies have enough star formation to trigger this feedback. That's where exotic dark matter particles enter the scene. What if dark matter isn't the simple, sluggish stuff we've assumed? Some models propose particles with a faint ability to interact with each other, not just through gravity but via an unknown force. These self-interacting particles would collide in the halo's crowded core, scattering like billiard balls and smoothing out the density. Others suggest dark matter might be fuzzy, made up of ultralight particles behaving more like waves than discrete dots, their inherent fuzziness preventing sharp cusps from forming. The core cusp problem isn't just a quirk, it's a potential crossroads. If star formation is the answer, it means ordinary matter has been quietly reshaping dark matter's domain all along. If exotic particles are to blame, we might be on the verge of uncovering entirely new physics. Either way, these fluffy cores are more than a glitch in the data. They're a clue that dark matter's story is far stranger and far more dynamic than we ever imagined. If dark matter truly fills the cosmos in a chaotic, isotropic haze, why do the Milky Way satellite galaxies line up like pearls on a cosmic string? This eerie alignment, known as the plane of satellites problem, defies one of cosmology's core expectations, that small galaxies should swirl around their hosts in a messy, three-dimensional swarm like bees around a hive. Instead, nearly all of the Milky Way's known satellites orbit within a razor-thin plane, a disk so precise it's as if some unseen hand arranged them with celestial precision. This isn't just a fluke of our local neighborhood. The same strange geometry appears around our galactic twin, Andromeda, where dwarf galaxies also cluster into a narrow plane. Statistically, the odds of this happening by chance are astronomically low, like tossing a handful of confetti and watching every piece land in a straight line. So what's bending the rules? One possibility stretches back to dark matter's cosmic web. Picture the universe's large-scale structure as a network of rivers with dark matter flowing along dense filaments. Galaxies form along these streams, and perhaps satellites are born from splinters of those primordial currents, inheriting their alignment like leaves caught in a river's flow. Yet even this elegant idea runs into turbulence. Supercomputer simulations based on the Lambda CDM model, our gold standard for cosmic evolution, struggle to recreate such extreme galactic flatness. If dark matter truly governs these orbits, why don't virtual universes in our computers mirror reality? Some theorists suggest we're missing a critical ingredient, like faint interactions between dark matter and gas during galaxy formation. Others propose a wilder idea, that these planes are fossilized relics of ancient collisions, where a past encounter with another galaxy shredded its satellites into a disk-like debris field. But the boldest hypothesis challenges Lambda CDM itself. Could our foundational model of dark matter be incomplete? Alternative theories, like modified gravity, claim these planes are natural outcomes of orbital dynamics, no invisible matter required. Yet even these alternatives falter when pressed to explain other dark matter phenomena, leaving us at a crossroads. The plane of satellites isn't just a curiosity, it's a potential crack in the foundation of modern cosmology, a sign that dark matter's story may be far richer and far weirder than we've dared to suppose. Every new dwarf galaxy discovered in this mysterious plane tightens the knot. Are we seeing the ghostly imprint of dark matter's hidden structure, or witnessing the slow unspooling of our most trusted cosmic theories? One thing's certain, the universe loves a good pattern, but it's up to us to decipher whether this one is a clue, a coincidence, or a cosmic prank. Dragonfly 44 isn't your typical galaxy. Floating in the Coma cluster 300 million light-years away, it spans the width of the Milky Way but glows with just 1% of its stars. Picture a cosmic phantom, a wispy, translucent veil of starlight, so faint it nearly vanished into the black until astronomers spotted it in 2014. This is an ultra-diffuse galaxy, or UDG, a celestial paradox, enormous in size yet barely there, and Dragonfly 44 isn't alone. Hundreds of these ghostly giants drift through the cosmos, defying every rule we thought we knew about how galaxies form and survive. What makes UDGs so baffling isn't just their faintness, it's what lurks beneath the surface. When researchers measured Dragonfly 44's motion, they found its stars whirling at dizzying speeds, suggesting a gravitational grip far stronger than its visible matter could provide. The verdict: this ethereal galaxy is 99.99% dark matter, a ratio so extreme it's like discovering a balloon held down by an invisible anvil. Most galaxies balance ordinary matter and dark matter like ingredients in a recipe, but UDGs toss out the rulebook, packing enough dark matter to anchor a Milky Way-sized beast while leaving almost nothing left to glow. How do these shadowy giants even exist? One theory suggests they're failed galaxies, islands of dark matter that struggle to attract enough gas to birth stars. Imagine a cosmic seed planted in barren soil, its potential stunted from the start. Another idea paints them as galactic survivors, stripped of their stars by violent encounters with neighboring clusters. Picture a shipwrecked vessel, its hull battered by tides, leaving only the densest parts intact. But some UDGs, like Dragonfly 44, reside in quiet corners of space, untouched by such chaos, deepening the mystery. The real shock came when astronomers found UDGs that shouldn't be alive. Without enough stars to heat their gas, these galaxies ought to collapse under their own weight, crumpling like paper in a fist. Yet they persist, their dark matter halos seemingly acting as cosmic Kevlar, shielding them from self-destruction. Even stranger, some UDGS host globular clusters, dense knots of ancient stars typically found in galaxies brimming with stellar firepower. It's as if these ghosts are wearing crowns meant for kings. The implications ripple far beyond these oddball galaxies. If dark matter can sculpt structures as delicate as UDGS, it might reshape our entire understanding of galactic evolution. Perhaps the cosmos is teeming with faint, unseen giants, their dark matter hearts invisible to our telescopes. Or maybe UDGS are the missing link between dwarf galaxies and cosmic titans, a hidden chapter in the universe's storybook. Every new discovery peels back another layer, revealing just how little we grasp about the invisible forces knitting the cosmos together. One thing's certain, ultra-diffuse galaxies are more than cosmic curiosities. They're stress tests for our theories, pushing dark matter's quirks into the spotlight. When a galaxy can be both massive and nearly invisible, it's a humbling reminder that the universe's playbook is far stranger than we've imagined, and that dark matter's secrets are written in the faintest ink imaginable. If dark matter is the universe's invisible glue, binding galaxies together with its gravitational might, then NGC 1052 DF2 is the cosmic rebel that refuses to play by the rules. Discovered in 2018, this ghostly galaxy, drifting 330 million light-years away, stunned astronomers with a claim that seemed impossible. It appeared to have no dark matter at all. Its stars moved sluggishly, as if untouched by the unseen hand that whips other galaxies into shape. The discovery sent shockwaves through astrophysics, because if dark matter isn't universal, what does that mean for everything we think we know? At first glance, DF2 looks like any other ultra-diffuse galaxy, a wispy, translucent sprawl of stars. But unlike Dragonfly 44, whose motions betrayed an overwhelming dark matter presence, DF2's stars crept along at a pace explained by visible matter alone. It was like watching a car roll downhill without an engine. The math simply didn't add up. Researchers double-checked the data, triple-checked it, yet the results held. DF2 seemed to be floating through space without dark matter's anchor. The immediate question was how. One camp argued for tidal stripping, the idea that a violent encounter with a neighboring galaxy, like the massive NGC 1052, might have ripped away DF2's dark matter. Picture a thief in the night, stealthily stealing only the invisible stuff while leaving the stars behind. Simulations show this is possible. As galaxies collide, dark matter, which doesn't clump like ordinary matter, can be tugged outward by gravity, leaving a stripped galaxy in its wake. But DF2 shows no obvious scars of such a traumatic past, no stretched-out tails of stars or gas to hint at a recent collision. Others wondered if the measurements themselves were flawed. Perhaps DF2's distance was miscalculated, skewing the star speed calculations. Or maybe its stars weren't tracing the galaxy's true gravitational field, instead orbiting in some peculiar, deceptive pattern. Yet follow-up observations only deepened the mystery. A second dark matter-deficient galaxy, DF4, was found nearby, followed by others in different corners of the cosmos. These outliers began to form their own eerie club galaxies that defy the dark matter paradigm. Then came the curveball: what if DF2 isn't the anomaly, but we are? A radical minority suggests dark matter might not be a particle at all, but a quirk of gravity itself, a theory called modified Newtonian dynamics, or MN. In this view, the odd motions of DF2 aren't a problem to solve, but proof that gravity behaves differently on galactic scales. Yet MN struggles to explain other dark matter phenomena, like the bullet cluster's gravitational lensing, where invisible mass clearly bends light. The debate rages, with each new observation fueling fresh arguments. The real puzzle isn't just DF2's missing dark matter, it's what its existence says about galaxy formation. If dark matter can be absent, does that mean it's not essential for birthing galaxies? Or does it hint at a more complex relationship where some galaxies form in ways we've yet to imagine? Every time we think we've pinned dark matter down, a galaxy like DF2 wriggles free, reminding us that the universe thrives on exceptions. For now, these enigmatic outliers stand as cosmic riddles, whispering that the story of dark matter and the galaxies it sculpts is far from finished. The universe isn't just expanding, it's doing so at a rate that's tearing apart the very foundations of cosmology. This is the Hubble tension, a glaring mismatch between how fast the cosmos should be growing versus how fast we see it happening. On one side, we have the early universe's baby picture, the cosmic microwave background, or CMB, which suggests a relatively modest expansion rate. On the other, modern measurements of supernova and pulsating stars scream that the universe is sprinting away faster than expected. The discrepancy is small but stubborn, like a clock that ticks just a few seconds too fast every hour. Over billions of years, those seconds add up, and suddenly our cosmic timeline is in chaos. Dark matter might be the silent architect of this rift. If it behaves differently now than it did in the universe's infancy, it could tweak the expansion rate in ways we haven't accounted for. Picture a thermostat stuck between two settings early on. Dark matter's gravity could have acted as a brake, slowing expansion as the CMB records. But if dark matter's influence has waned over time, or if it interacts with dark energy in unexpected ways, that brake might have loosened, letting the universe accelerate beyond predictions. But how? One tantalizing idea is that dark matter isn't entirely stable. What if some of it decays into lighter particles or even into dark energy itself? This wouldn't just alter the universe's expansion history, it'd rewrite dark matter's role from passive scaffolding to an active player in cosmic evolution. Imagine building a bridge where the girders slowly transform into fuel for the river's current. The structure itself would warp in ways no engineer could anticipate. Then there's the wild card, dark matter's temperature. Most models treat it as cold, slow-moving and clumpy, but if it's warmer or more dynamic than we thought, its distribution across cosmic time could shift, subtly altering how it tugs on the universe's fabric. Alternatively, dark energy might not be the constant force we've assumed. If it strengthens over time, it could overpower dark matter's grip earlier than expected, yanking the expansion rate off script. The Hubble tension isn't just a numbers game, it's a crack in the door hinting that dark matter, and perhaps the entire standard model of cosmology, is due for a rewrite. Every conflicting measurement is a flash of lightning, illuminating just how much we still don't understand about the invisible forces shaping reality. If the universe's expansion rate is a song, we're still learning the notes, and dark matter might be the key to why the melody keeps changing. Deep in the heart of our galaxy, something invisible is screaming. Not with sound, but with gamma rays, blasts of light so energetic they pierce through cosmic dust like bullets through paper. For years, telescopes have detected a bizarre excess of these gamma rays flooding from the Milky Way's core, a glow that shouldn't exist if only ordinary stars and gas were at work. The culprit, one of dark matter's most tantalizing possibilities, annihilation. Imagine dark matter particles as cosmic ghosts drifting through space, oblivious to everything including each other except for gravity's pull. But what if just occasionally they do interact? If certain theories are right, when two dark matter particles collide, they could annihilate in a flash of energy, morphing into gamma rays we might detect. It's like watching shadows crash together and burst into sparks. The galactic center, dense with dark matter, would be the perfect furnace for these fireworks. But the plot thickens. Not all scientists are convinced. Alternative explanations lurk in the shadows, like millisecond pulsars, dead stars spinning wildly, spewing gamma rays like lighthouses in the dark. These celestial powerhouses could mimic the signal, their collective glow blending into a false positive. Worse yet, our telescopes might be playing tricks on us. Gamma-ray detectors aren't perfect. They can misread noise for signal or confuse distant astrophysical phenomena with something far more exotic. The debate hinges on subtle fingerprints. Dark matter annihilation should produce a smooth, symmetrical gamma-ray haze centered on the galaxy's core, while pulsars would leave clumps, bright spots strewn like breadcrumbs. Recent observations tease both patterns, keeping the mystery alive. Some researchers argue for a hybrid solution. Maybe it's mostly pulsars with a dash of dark matter annihilation mixed in. Others are hunting for a smoking gun, a telltale energy spike in the gamma rays that could only come from specific dark matter particles. What makes this hunt so thrilling is the staggering implication. If annihilation is real, we're not just mapping dark matter's presence, we're witnessing its death throes. Every flicker of excess gamma rays could be a cosmic gravestone, marking where invisible particles met their end. Yet until we untangle pulsars from potential dark matter signals, the galactic center's glow remains a riddle wrapped in an enigma, one that could either crack open particle physics or force us back to the drawing board. The stakes couldn't be higher. Solve this and we might finally grasp dark matter's true nature. Fail, and the universe's biggest secret slips deeper into the shadows. For now, the gamma rays keep pouring in, silent sirens calling us toward an answer just out of reach. Our galaxy, the Milky Way, is often pictured as a shimmering, flat spiral, a cosmic frisbee spinning gracefully through space. But its dark matter halo, the invisible cocoon that surrounds it, might be anything but symmetrical. Recent studies suggest this halo is warped, lopsided, like a deflated balloon with one side bulging oddly outward. This isn't just a cosmic quirk, it's a clue that our galaxy's history is messier, more violent than we ever imagined. The evidence comes from the motions of stars and satellite galaxies orbiting the Milky Way. Like bees tracing the shape of a hidden flower, their paths reveal the gravitational imprint of the dark matter halo, and something's off. Instead of moving in predictable, balanced orbits, some stars seem tugged toward an unseen asymmetry, as if the halo's mass is piled heavier on one side. Even more telling, the Milky Way's outer gas disk is warped, its edges twisting upward on one side and downward on the other, like a record left too long in the sun. What could bend an entire dark matter halo? One leading suspect: ancient collisions. Imagine a dwarf galaxy, rich in dark matter, plowing into the Milky Way billions of years ago. Like a stone tossed into a pond, the impact would send ripples through our halo, sloshing its mass unevenly. Over time, the disturbance might settle, but not perfectly. Some simulations show these imbalances can persist for eons, frozen into the halo's structure like a cosmic fingerprint. But there's a twist. The warping might not be ancient history, it could be ongoing. Right now, the Milky Way is digesting the Sagittarius dwarf, a small galaxy caught in a death spiral around us. Each pass tears Sagittarius apart, scattering its stars and dark matter into chaotic streams. Some researchers think these repeated encounters could be actively deforming our halo, like a sculptor kneading clay. If true, the Milky Way isn't just a serene island universe, it's a dynamic beast still reshaping itself with every galactic bite it takes. Then there's the darkest possibility. What if the lopsidedness isn't from collisions at all? Alternative theories suggest dark matter itself might behave differently than we've modeled, clumping unevenly or responding to unseen forces. Could the halo's warp be a sign that dark matter isn't just passive scaffolding, but an active, evolving entity? The data isn't conclusive, but the implications are staggering. This isn't just about the Milky Way. If our halo is askew, others might be too, reshaping how we understand galaxies across the cosmos. A warped halo could alter star formation, bend the paths of cosmic rays, even redirect entire streams of gas falling into galaxies. The universe, it seems, doesn't do perfect symmetry, and in that imperfection, we might finally find the key to dark matter's greatest secrets. Dark matter might not just be invisible, it could be weird in ways that defy our understanding of quantum physics itself. While we've long imagined it as a sea of sluggish, undiscovered particles, other possibilities lurk in the shadows. What if dark matter isn't a particle at all, but a swarm of primordial black holes forged in the chaos of the Big Bang? Or perhaps it's made of actions, hypothetical particles so light they barely interact with reality, or sterile neutrinos, ghostly cousins to the neutrinos we know, slipping through matter like it's not even there. Each candidate opens a door to a stranger universe, and the race to find out which one is real is already underway. Primordial black holes are the cosmic wildcards. Unlike the black holes born from dying stars, these would have formed in the first microseconds of the universe, when extreme densities could have crumpled matter into tiny, dense knots. Ranging from the mass of a mountain to thousands of suns, they'd be invisible unless they passed between us and a distant star, bending its light like a lens. Experiments like OGLE and HSC scan the skies for these fleeting microlensing events, but so far, the numbers don't add up to explain all of dark matter. Yet the idea refuses to die. Some theorists suggest smaller, asteroid mass black holes could still be hiding in the data, their subtle gravitational whispers drowned out by cosmic noise. Then there's the action, a particle born not from observation but from mathematical necessity. In the 1970s, physicists wrestling with quirks in quantum chromodynamics, the rules governing quarks proposed an ultra-light particle to restore symmetry. Actions fit dark matter's bill perfectly. They'd barely interact with ordinary matter, yet their sheer numbers could outweigh everything else in the cosmos. Detecting them is like trying to catch mist with a sieve. Projects like ADMX or the Action Dark Matter Experiment use powerful magnetic fields to coax actions into revealing themselves, converting into faint microwave photons under just the right conditions. It's a needle in a haystack hunt, but if successful, it could solve two cosmic puzzles at once. Sterile neutrinos are even more elusive. Ordinary neutrinos are already phantom-like, streaming through the universe with barely a whisper. Sterile neutrinos would take this to the extreme, interacting only via gravity. Some theories suggest they could decay into X-rays, leaving behind a faint glow in galaxy clusters, tantalizing hints like the 3.5 kiloelectronvolt line spotted in Andromeda's core. But conclusive proof remains just out of reach, tangled in debates over instrumental noise and astrophysical backgrounds. Meanwhile, detectors like LUX Zeppelin are digging for the more traditional suspects, WIMP or weakly interacting massive particles. Buried a mile underground in abandoned gold mines, these experiments wait for the once-in-a-lifetime moment a dark matter particle bumps into an atomic nucleus, releasing a flicker of light or heat. So far, the silence is deafening. Each null result tightens the constraints, boxing dark matter into smaller, stranger corners of possibility. The truth might lie in a combination or something entirely unforeseen. Dark matter's quantum nature could be a tapestry of these ideas, woven together in ways we've yet to untangle. Every experiment, from the colossal to the minuscule, is a torch probing the darkness, and with each passing year, the universe's biggest secret feels just a little closer to being told. Picture the universe not as scattered islands of light, but as a vast, interconnected tapestry, one woven from threads so faint they're invisible to our eyes. These are the filaments of the cosmic web, dark matter's sprawling architecture that stretches between galaxies like ghostly bridges across the void. While stars and gas paint the visible universe, it's this hidden scaffolding that dictates where galaxies form, how they cluster, and even the fate of their collisions. We've long suspected dark matter's web-like structure, but proving it required a clever trick of physics, gravitational lensing. When light from distant galaxies travels through the cosmos, it doesn't move in straight lines. It bends around massive objects warped by gravity's pull. Dark matter, though invisible, has mass and thus distorts spacetime like a weight placed on a trampoline. By studying how billions of background galaxies appear subtly stretched, their shapes twisted as if viewed through old glass, astronomers can map the unseen mass between them. The result, a three-dimensional blueprint of the cosmic web, its filaments glowing not with light but with the fingerprints of gravity. These maps reveal something extraordinary. Dark matter doesn't just lurk in halos around galaxies. It forms rivers of density, flowing between clusters in delicate, thread-like structures. Some filaments stretch hundreds of millions of light years, thinner than spider silk in proportion, yet massive enough to bind entire superclusters together. The Coma cluster, for instance, sits at the intersection of several such threads, a cosmic metropolis fed by dark matter's hidden highways. But how do these filaments shape the universe we see? Think of them as celestial nurseries. Where dark matter's rivers intersect, gravity pulls gas and dust into dense knots, sparking the birth of galaxies. Without this underlying web, matter would drift aimlessly, never clumping tightly enough to ignite stars. Simulations show that galaxies align along filaments like pearls on a string, their fates entwined with the web's structure. Even now, the Milky Way is likely gliding along a dark matter filament, drawn toward the immense gravitational pull of the Laniakea supercluster, yet mysteries linger. Some filaments appear denser than predicted, as if dark matter clumps more tightly along these threads than our models allow. Others seem oddly sparse, raising questions about whether dark matter interacts with itself in ways we've yet to imagine. Then there's the puzzle of orphan galaxies, isolated stars found far from any filament, floating in voids. How did they form without the web's guiding hand? The cosmic web isn't just a static backdrop, it's a dynamic, evolving entity. Collisions between filaments can send shockwaves through the gas they contain, heating it to millions of degrees, a process that might explain the searing intergalactic plasma we detect in X-rays. Meanwhile, the web's largest strands act as cosmic conveyor belts, funneling galaxies toward clusters in a slow-motion ballet that unfolds over billions of years. What's perhaps most humbling is the scale of our ignorance. We've barely begun to chart this invisible lattice, and every new map unveils fresh surprises. The cosmic web isn't merely dark matter's structure. It's the universe's hidden circulatory system, pulsing with gravitational tides we're only starting to trace. And as we peer deeper into its shadows, we might finally understand how darkness built the light. Fast radio bursts are cosmic enigmas, blisteringly bright flashes of radio waves that last mere milliseconds, yet pack more energy than the sun emits in days. These mysterious signals race across the universe, stretching and distorting as they pass through clouds of electrons in their path. But what if that distortion holds a clue to something far stranger? Astronomers are beginning to suspect fast radio bursts might be lighting the way to dark matter, turning these fleeting cosmic sparks into probes for the invisible fabric of the cosmos. When a fast radio burst travels through space, its journey leaves fingerprints. Different frequencies arrive at slightly different times, a phenomenon called dispersion. By measuring this delay, scientists can calculate how much material the burst passed through, like counting tree rings to gauge a forest's age. But some bursts show far more dispersion than visible matter can explain, as if they've traveled through hidden pockets of charged particles. This excess could be dark matter's calling card. One provocative theory suggests decaying dark matter particles might leave behind trails of ionized gas, subtle obstacles that tweak passing radio waves. Picture a ghostly fog, invisible to telescopes but detectable only when a burst of energy slices through it. Then there's the stranger possibility, cosmic strings. These hypothetical defects in space-time, thinner than an atom but stretching across the universe, could theoretically form from dark matter's quirks in the early cosmos. If a fast radio burst grazes such a string, its signal might twist or split in telltale ways, an echo of the universe's primordial fractures. It's a fringe idea, but in the hunt for dark matter, even the wildest leads deserve attention. Of course, not every unexplained dispersion signal points to dark matter. Magnetar's highly magnetized neutron stars remain the leading suspects for most fast radio bursts, and their chaotic environments could mimic some of these anomalies. The challenge lies in separating astrophysical noise from potential dark matter whispers. New telescopes like the CHIME array in Canada are cataloging thousands of bursts, hunting for patterns that might betray the unseen. A single burst with the right dispersion signature could rewrite the rules, turning these cosmic flashes into the ultimate dark matter detectives. What makes this search so thrilling is its sheer audacity. Fast radio bursts were once pure astrophysical puzzles. Now they might be the key to mapping the universe's darkest secrets. Whether they reveal decaying particles, cosmic strings, or something entirely unforeseen, one thing's clear. When the cosmos sends us a signal, even the briefest flicker can illuminate the deepest shadows. The Andromeda Galaxy isn't just our closest galactic neighbor. It's a dark matter detective's dream. Unlike the Milky Way's subtle, warped halo, Andromeda's dark matter cloak stretches far beyond its visible starlight, enveloping the galaxy in a sprawling, luminous shroud of gamma rays. This eerie glow, detected by NASA's Fermi telescope, isn't just cosmic static. It might be the signature of dark matter particles annihilating at the galaxy's edge, a process that could rewrite the rules of particle physics. But why does Andromeda's halo blaze so brightly while the Milky Way's remains comparatively dim? One clue lies in their collision histories. Andromeda has been a galactic glutton, devouring smaller galaxies and their dark matter halos over billions of years. Each merger would have stirred its halo into a swirling frenzy, increasing the chances of dark matter particles smashing together. Picture a snow globe shaken violently. Every flake collides more often, just as dark matter might in Andromeda's chaotic periphery. The Milky Way, though no stranger to cosmic cannibalism, has likely feasted more modestly, leaving its halo quieter, its particles drifting farther apart. Then there's the puzzle of scale. Andromeda's gamma-ray emission isn't just stronger. It extends nearly 2 million light-years from its core, far beyond where its stars fade into blackness. If dark matter is the source, this suggests its halo is vastly larger than predicted, a diffuse cloud clinging to the galaxy like an invisible atmosphere. Some models hint that Andromeda's halo might even brush against our own, their dark matter tendrils already intertwining in the cosmic dark, a preview of the titanic merger awaiting both galaxies 4 billion years from now. Yet not everyone is convinced the gamma rays point to dark matter. Alternative explanations lurk in the shadows. Pulsars, those rapidly spinning stellar corpses, could be the culprits, their collective emissions mimicking a smooth halo glow. Or perhaps the signal comes from cosmic rays, charged particles accelerated by supernova colliding with interstellar gas. The challenge is teasing apart these possibilities. One telling clue: the gamma ray's distribution. Dark matter annihilation should create a symmetrical haze, while astrophysical sources like pulsars would clump unevenly. So far, the data teases both patterns, keeping the debate alive. What makes Andromeda's halo so compelling isn't just its anomalies, it's the chance to study dark matter in a mirror galaxy. By comparing its structure to the Milky Way's, astronomers can ask, are these differences due to environment, history, or something intrinsic to dark matter itself? Every new observation peels back another layer, revealing that even in the darkest corners of the universe, no two galaxies tell the same story. Deep in the hearts of galaxy clusters, where matter crowds together in swirling maelstroms of gas and dust, telescopes have picked up an eerie signal, a faint X-ray whisper at exactly 3.5 kiloelectronvolts. This spectral line, first spotted in the Perseus cluster in 2014, shouldn't exist based on our current understanding of astrophysical processes. Yet there it glows, persistent and unexplained, like a candle flickering in a sealed vault. Some researchers believe this could be the long-sought decay signature of sterile neutrinos, a hypothetical dark matter candidate so elusive it barely interacts with the known universe. If confirmed, it would mark the first direct detection of dark matter's ghostly presence. The sterile neutrino theory is elegant in its simplicity. These particles, if they exist, would occasionally decay into ordinary neutrinos and photons, with the energy of those photons landing precisely at 3.5 kiloelectronvolts. Picture a radioactive element slowly breaking down, emitting gamma rays as it transforms. Sterile neutrinos would do the same, but across cosmic time and space, their collective decay painting the universe with this specific X-ray hue. Galaxy clusters dense with dark matter would naturally amplify the signal, turning them into cosmic beacons for this subtle glow, but the cosmos rarely offers straightforward answers. Skeptics point to more mundane explanations rooted in plasma physics. Hot, ionized gas within clusters reaching temperatures of millions of degrees can produce complex atomic transitions, including X-ray lines we haven't fully catalogued. Potassium and chlorine ions, for example, emit close to 3.5 kiloelectronvolts when they shed electrons under extreme conditions. Could the signal simply be a quirk of turbulent plasma, misidentified as dark matter's fingerprint? The debate hinges on subtle details. If the 3.5 kiloelectronvolt line appears consistently across multiple clusters, especially in regions with minimal hot gas, the dark matter hypothesis gains credence. Yet observations remain frustratingly ambiguous. Some clusters, like Perseus and Centaurus, show a strong signal, while others, like Coma, display nothing at all. Even within single clusters, the line's intensity varies unpredictably, patterns that don't neatly align with sterile neutrino decay models. Adding to the confusion, Earth-bound X-ray detectors aren't perfect. Their sensitivity peaks and dips across different energy ranges, and background noise can mimic or obscure faint signals. When one team claimed to detect the line in our own Milky Way's halo using XMM Newton data, others questioned whether instrumental artifacts or even solar-wind interactions might be to blame. The line between discovery and delusion is razor-thin when hunting something as elusive as dark matter's decay. What makes this mystery so compelling isn't just the potential payoff, it's the sheer ingenuity of the hunt. To test the sterile neutrino idea, astronomers have turned to dwarf galaxies, which are dark matter-dominated and nearly gas-free. If the 3.5 kiloelectronvolt line appears there where hot plasma is absent, it would be a near smoking gun. Preliminary studies of the Draco and Ursa Minor dwarfs hint at something intriguing, but the signal is too weak to declare victory. Meanwhile, particle physicists are designing lab experiments to chase sterile neutrinos directly, hoping to catch them in the act of oscillation, a process that could bridge the visible and invisible worlds. Even if the line ultimately fades into the noise of astrophysical chatter, its legacy will endure. It's forced us to refine our models of both plasma physics and dark matter, to question assumptions and to explore uncharted corners of the X-ray spectrum. Whether the glow is a mirage or a milestone, it reminds us that the universe's darkest secrets often hide in the faintest flickers of light. The bullet cluster isn't just a cosmic collision. It's a courtroom where dark matter's existence was proven beyond reasonable doubt. Two massive galaxy clusters, each hundreds of millions of light-years wide, slammed into one another at millions of miles per hour, creating one of the most energetic events in the known universe. But what made this collision historic wasn't the chaos of stars and gas, it was the eerie calm of something unseen. When astronomers mapped the aftermath using gravitational lensing, they found the unthinkable. The cluster's dark matter had sailed smoothly through the crash, leaving the visible matter behind like smoke trailing a bullet. Here's why that's revolutionary. When these clusters collided, their interstellar gas, the visible matter, piled up in the center, heated to blistering temperatures by the impact. But their stars, spaced too far apart to touch, passed through mostly unscathed. Dark matter, if it behaved like normal matter, should have followed the gas, clumping where gravity was strongest. Instead, the lensing maps revealed dark matter's halos drifting ahead of the wreckage, their gravity bending light from background galaxies as if nothing had happened. It was like watching two ghosts walk through a wall while their clothes got tangled on the other side. This separation holds the key to dark matter's nature. Unlike ordinary matter, which interacts via electromagnetism and slows down during collisions, think of two clouds of smoke merging. Dark matter feels only gravity. It doesn't stick or scatter, it simply keeps moving, indifferent to the chaos around it. The bullet cluster became the first direct evidence that dark matter isn't just an anomaly in galaxy rotations. It's a physical substance, one that outnumbers visible matter 5 to 1. Critics of dark matter, particularly supporters of modified gravity theories like Mund, were left scrambling. No adjustment to gravity's laws could explain why the lensing signal, the fingerprint of mass, divorced itself so cleanly from the visible wreckage. But the bullet cluster's secrets don't end there. Recent studies suggest the collision might also reveal how dark matter interacts with itself. Some models predict dark matter particles could occasionally bump into one another, creating drag. If so, the halos in the bullet cluster should show slight distortions, hints of friction. Yet so far they appear flawless, suggesting dark matter is even more aloof than we thought. It's a paradox. The stuff that holds galaxies together might be utterly indifferent to everything, even itself. What makes this cosmic crime scene so compelling is its universality. Since the bullet cluster, astronomers have found similar separations in other mergers, like MAX J0025.7-1222, nicknamed the baby bullet. Each collision replays the same story. Dark matter moves to its own rhythm, silent and unstoppable, while visible matter pays the price in fire and turbulence. These aren't just fireworks, they're forensic snapshots of a hidden universe, proving that darkness isn't the absence of matter, it's the stage upon which light dances. The bullet cluster didn't just confirm dark matter's existence, it redefined how we see the cosmos. Galaxies aren't the universe's true structure, they're glitter scattered across a scaffold we can't see. And when that scaffold reveals itself, as it did here, it humbles us with the realization that most of reality doesn't just elude our sight. It operates by rules we're only beginning to decipher. If dark matter had a resume, its top qualification would be architect of the universe, the invisible force that built the stage for life itself. Without its gravitational scaffolding, galaxies wouldn't have clumped together in the early cosmos, stars wouldn't have ignited, and planets like Earth might never have formed. The atoms that make up our bodies were forged in stellar furnaces, but those furnaces only lit because dark matter first gathered the gas to fuel them. It's a humbling thought. We owe our existence to something we can't see, touch, or even fully comprehend. Take the Milky Way's birth as an example. Over 13 billion years ago, our galaxy began as a faint ripple in the cosmic web, a knot where dark matter's threads crossed. Gravity amplified that knot, pulling in hydrogen until it collapsed into stars that would later explode, scattering heavier elements like carbon and oxygen into space. Without dark matter's patient pull, that gas might have drifted forever, too diffused to ignite. Even now, our solar system orbits within a vast dark matter halo, its gravity silently shaping the paths of comets and asteroids, subtly guiding the chaos of the cosmos. But here's the mind-bending question: could dark matter itself host life? Most theories dismiss the idea. After all, it doesn't form atoms, molecules, or any of the chemistry we recognize. Yet nature thrives on complexity. What if dense dark matter halos trap exotic particles that interact in ways we've never imagined? Some speculative models suggest dark planets could exist, bound not by electromagnetic forces but by dark matter's gravity alone. These wouldn't be rocky worlds but shadowy spheres of pure gravitational influence, their landscapes forever invisible to our eyes. Then there's the wild card, sterile neutrinos. If these hypothetical dark matter particles occasionally decay, they might release tiny bursts of energy enough to power bizarre, slow-motion biochemical reactions in environments utterly alien to Earth. Picture life not as DNA and water, but as ripples in dark matter's quantum field processing information over cosmic timescales. It's a fringe idea, but the universe has surprised us before. Whether or not dark matter harbors its own forms of life, one truth remains: without it, our kind of life wouldn't be here. Every galaxy, every star, every planet is a testament to its quiet power. The next time you look up at the night sky, remember, you're not just seeing stars, you're witnessing the aftermath of a cosmic construction project, one where darkness did all the heavy lifting. Galaxies don't glide through the cosmos untouched, they leave footprints in the dark. Astronomers have spotted something eerie trailing behind certain galaxies, especially those barreling through dense clusters. Faint, ghostly wakes of dark matter stretched out like cosmic shadows. It's as if these galaxies are ships plowing through an invisible sea, their gravitational pull stirring up waves we can't see but can feel in the way they bend space-time around them. This phenomenon, called dynamical friction, isn't just a curiosity. It's a window into how dark matter halos evolve over billions of years, and how the universe's hidden architecture reshapes itself in real time. Picture a galaxy diving into a crowded cluster, its immense gravity tugging at the surrounding dark matter. Just as a speedboat churns water in its wake, the galaxy drags dark matter particles along its path, creating an overdensity, a ripple behind it. Unlike water, though, these ripples don't fade. Dark matter's gravitational pull acts like cosmic glue, causing the galaxy to slow ever so slightly, as if space itself were pushing back. Over millennia, this subtle braking effect can alter a galaxy's orbit, nudging it toward the cluster's heart like a leaf spiraling into a drain. The smoking gun for these wakes comes from gravitational lensing. When light from distant objects warps around a galaxy cluster, the distortion maps the mass distribution, including the unseen dark matter. In clusters like Able 2163, astronomers have spotted telltale asymmetries. The lensing signal isn't smooth. Instead, it's as if someone smudged the halo's edge, leaving streaks of extra mass trailing behind certain galaxies. These aren't random flaws in the data, they're the fingerprints of dynamical friction at work. But here's where the mystery deepens. Not all galaxies leave wakes, and some wakes are far stronger than expected. The difference might lie in the dark matter itself. If dark matter particles can interact weakly with each other beyond just gravity, those interactions could amplify the wake, like wind whipping up a boat's trail into choppier waves. Alternatively, the galaxy's own structure might play a role. A massive, compact galaxy could plow through dark matter more disruptively than a diffuse one, just as a cruise ship creates a larger wake than a kayak. These wakes aren't just passive relics, they're active players in cosmic evolution. As a galaxy's wake grows, it can siphon dark matter from the surrounding halo, subtly reshaping the cluster's gravitational landscape. Over time, this redistribution might funnel more galaxies toward the cluster's center, fueling collisions and mergers that ignite bursts of star formation. It's a domino effect, one where dark matter, the universe's most aloof substance, becomes the unseen hand guiding the fate of galaxies. The implications stretch far beyond individual clusters. If dark matter wakes are common, they could explain why some galaxies seem to precess in their orbits, their paths slowly twisting like wobbly tops. They might even shed light on the ultimate fate of our own Milky Way, which will one day plunge into the Andromeda Galaxy's dark matter halo. Will we leave a wake of our own? And if so, will it dictate how our merger unfolds, whether we spiral into chaos or settle into a new, stable orbit? For now, these questions linger at the edge of our understanding. Every new observation of a dark matter wake peels back another layer, revealing a universe far more dynamic and far stranger than we ever imagined. The cosmos isn't just expanding, it's stirring, swirling, and settling like a vast, invisible ocean, with galaxies as the ships and dark matter as the tide. And we're only just beginning to read the waves. The Triangulum Galaxy, our Milky Way's petite cosmic neighbor, should be a textbook case of dark matter's universal reach, a smaller galaxy wrapped in a proportionally smaller halo. But when astronomers peered into its depths, they found something off. Unlike the sprawling, massive halos of galaxies like Andromeda or the Milky Way, Triangulum's dark matter cloak seems oddly underdressed. It's as if the universe forgot to pack its full gravitational punch, leaving astronomers to wonder, do small galaxies play by different rules, or is there something we're fundamentally missing about how dark matter clumps together? Scale should dictate everything in cosmology. Larger galaxies, with their vast stellar populations and immense gravity wells, ought to attract proportionally larger dark matter halos. And for the most part, they do. The Milky Way's halo stretches hundreds of thousands of light years beyond its visible disk, while Andromeda's might brush against ours already. But Triangulum, though it boasts 40 billion stars, making it no cosmic lightweight, defies expectations. Measurements of its rotation curve, which plots how fast stars orbit at different distances from the center, reveal a gravitational pull weaker than the visible mass alone can explain. It's the inverse of the dark matter problem we see in larger galaxies. Instead of stars whirling too fast, they're moving too slow, as if the halo's grip is slipping. One theory digs into Triangulum's turbulent past. Galactic collisions can strip away dark matter, much like peeling layers from an onion. Simulations suggest that if Triangulum had a close encounter with Andromeda, its far more massive neighbor tidal forces could have siphoned off chunks of its halo, leaving it anomalously light. Picture a smaller ship sailing too close to a battleship's wake, its cargo tossed overboard by the larger vessel's gravitational swell. Supporting this, astronomers have spotted faint stellar streams around Triangulum, possible debris from such an encounter. Yet not all the evidence fits. Some models show that even after a violent interaction, dark matter halos rebound, their particles diffusing back into equilibrium. Triangulum's halo shouldn't look this sparse. Then there's the radical possibility. Dark matter's distribution isn't scale invariant. Maybe the physics governing how it clumps changes below a certain galactic mass threshold. Smaller halos could be fluffier, their particles warmer or more mobile, resisting the dense central cusp seen in larger galaxies. This would parallel the too big to fail problem in reverse, small galaxies failing to hold onto the dark matter they should theoretically harbor. Alternatively, Triangulum's halo might be rich in self-interacting dark matter, where particles collide and scatter, smoothing out the density over time like sand settling in a shaken jar. The stakes here are higher than just one galaxy's oddities. If Triangulum's halo breaks the rules, it could imply that dark matter's behavior is far more nuanced than our blunt cosmological models account for. Perhaps its properties vary depending on environment, like water behaving differently in a cup versus an ocean. Or maybe smaller halos are more susceptible to disruption, not just by visible matter, but by the dark cosmos itself. Every anomaly in Triangulum's shadowy shroud forces us to ask, is dark matter's story universal, or are we stitching together a patchwork quilt from threads we don't fully understand? What makes this mystery so compelling isn't just the scientific implications, it's the sheer irony. The Triangulum Galaxy, often overshadowed by its flashier neighbors, might hold the key to unraveling one of dark matter's most persistent puzzles. In its quiet defiance of expectation, it reminds us that the universe reserves its deepest secrets not for the grandest stages, but for the unassuming corners we might otherwise overlook. Dark matter might be cold, but what if it's not as sluggish as we've assumed? The debate over its temperature isn't about degrees on a thermometer. It's about speed, motion, and how this invisible substance sculpted the early universe. Cold dark matter, the reigning theory, paints these particles as slow-moving heavyweights, clumping easily under gravity's pull to form the cosmic web's dense knots. But warm dark matter offers a twist: lighter, faster particles that could solve some of cosmology's thorniest puzzles if they exist. The evidence hinges on two cosmic fingerprints: the Lyman alpha forest and the dwarf galaxy paradox. Picture the light from a distant quasar, a brilliant beacon billions of light years away. As that light journeys through the universe, it passes through clouds of hydrogen gas, each absorbing specific wavelengths and leaving dark lines in the quasar's spectrum. These lines, stacked like tree rings, form the Lyman alpha forest, a record of hydrogen distribution across cosmic time. Cold dark matter predicts a specific pattern: sharp, dense peaks from gas clumped around dark matter's gravitational wells. Yet some observations show smoother distributions, as if something prevented matter from piling up too tightly, exactly what warm dark matter's quicker, more energetic particles would do. Then there's the dwarf galaxy problem. Cold dark matter simulations predict swarms of tiny satellite galaxies around Milky Way like giants, but reality delivers far fewer. Warm dark matter's lighter particles would move fast enough to suppress small-scale clumping, leaving fewer dwarf galaxies in their wake. It's like comparing snowfall to rain. Cold dark matter is the snow, settling into dense drifts, while warm dark matter is the rain, dispersing more evenly. Some ultra-faint dwarfs, barely clinging to existence, might even be the warm model smoking gun galaxies so tenuous they only formed where dark matter's faster motions allowed. But the case isn't closed. Critics argue that astrophysical feedback, supernova blasting gas out of small galaxies, could mimic warm dark matter's effects, thinning the dwarf population without altering dark matter's nature. Others point to discrepancies in the Lyman alpha data, where alternative explanations like turbulent gas dynamics might skew the results. Meanwhile, particle physics complicates things further. Warm dark matter candidates like sterile neutrinos remain theoretical phantoms, their existence still unproven despite decades of hunting. The stakes are cosmic. If dark matter is warm, it could rewrite the story of structure formation, explaining why some corners of the universe look oddly smooth. If it's cold, we'll need new ideas to reconcile theory with observation. Perhaps dark matter isn't one thing but many, a mix of temperatures shaping the cosmos in tandem. Every new observation, from dwarf galaxy surveys to quasar light, chips away at the mystery, but the truth remains just out of reach. What makes this debate so electrifying isn't just the science, it's the humility it demands. We're peering back to the universe's infancy, trying to decode the behavior of particles we've never seen, using clues written in the faintest light and the scarcest stars. Whether dark matter is cold, warm, or something stranger altogether, each answer and every contradiction brings us closer to understanding the invisible hand that built everything we know. The Large Magellanic Cloud isn't just another satellite galaxy drifting lazily around the Milky Way. It's a cosmic wrecking ball trailing an invisible cloak of dark matter, and its gravitational wake might rewrite the story of our galactic neighborhood. For centuries, astronomers viewed this hazy patch in the southern sky as a quiet companion, a dwarf galaxy content to orbit at a safe distance. But recent observations reveal something far more dramatic. The Magellanic Cloud's dark matter halo is colossal, stretching across hundreds of thousands of light years, and it's already colliding with our own. The collision isn't violent. Dark matter passes through itself like a ghost, but its gravitational ripple effects could be reshaping the Milky Way in ways we're only beginning to understand. This isn't just a slow-motion dance between two galaxies. The Magellanic Cloud's halo is so massive that some scientists argue it shouldn't even be classified as a dwarf galaxy. Unlike other small satellites which cling to their dark matter like faint shadows, the cloud's halo rivals some full-fledged galaxies, a mismatch that raises eyebrows. How did such a small collection of stars gather so much dark matter? One theory points to a history of galactic theft. The cloud might have cannibalized smaller galaxies over billions of years, absorbing their halos into its own. Picture a sponge soaking up droplets, each merger adding to the cloud's invisible bulk while leaving its starlight relatively unchanged. Then there's the footprint it's leaving on the Milky Way. As the Magellanic Cloud barrels through our galaxy's dark matter halo, it tugs on the fabric of space-time, creating a wake, an overdensity of dark matter trailing behind it like the ripples behind a speedboat. This wake isn't just a curiosity, it's a gravitational anchor, subtly altering the orbits of stars and gas within the Milky Way. Some researchers believe it could even explain strange, unexplained warps in our galaxy's outer disk, as if the dark matter wake is pulling the Milky Way's edges out of alignment. The most startling revelation, though, is the cloud's trajectory. For decades, we assumed it was on a stable, long-term orbit around the Milky Way. But precise measurements from missions like Gaia now suggest it's moving faster than escape velocity, meaning it might not be a permanent satellite at all. Instead, the Magellanic Cloud could be on its first fateful pass near our galaxy, a chance encounter that will eventually fling it back into intergalactic space. If true, its current collision with our dark matter halo isn't part of a recurring cycle but a once-in-a-lifetime event, a fleeting gravitational handshake between two galaxies that barely know each other. What does this mean for the future? If the Magellanic Cloud is indeed a newcomer, its dark matter halo could be stirring up our galaxy's own halo in unprecedented ways. Simulations show that such an intrusion might kick dark matter particles into new orbits, redistributing mass in ways that could affect everything from star formation to the Milky Way's eventual merger with Andromeda. Some models even suggest the cloud's passage could funnel dark matter toward the solar system, potentially increasing the odds of detecting these elusive particles here on Earth. The irony is profound. The large Magellanic Cloud, long dismissed as a bit player in the Milky Way story, might instead be a catalyst for cosmic change. Its dark matter halo isn't just a silent companion, it's a dynamic force reshaping our galaxy's hidden architecture in real time. And as we trace its unseen influence, we're reminded that even the faintest smudges of light in the night sky can harbor the universe's deepest secrets. What if dark matter isn't the steadfast, unchanging force we've assumed? The very idea that its density or behavior could shift over time sounds like science fiction, yet a growing number of scientists are entertaining this radical notion. Imagine the universe's hidden scaffolding subtly warping as eons pass, its influence ebbing and flowing like cosmic tides. This isn't just theoretical daydreaming. It could solve two of astronomy's biggest headaches: the Hubble tension's conflicting expansion rates and the baffling diversity of galaxy evolution across cosmic epochs. Take the Hubble tension first. If dark matter's gravitational pull weakened over time, perhaps because some of it decayed into dark energy or other particles, the universe's expansion rate could accelerate beyond early universe predictions. Picture a rope slowly fraying. At first, it holds tension firmly, but as strands snap, the remaining fibers bear more strain until the entire system shifts. Similarly, if dark matter's grip on the cosmos relaxed even slightly over billions of years, galaxies would drift apart faster, matching the runaway expansion we observe today. But time-varying dark matter could also explain why ancient galaxies look nothing like their modern counterparts. The James Webb Space Telescope has spotted massive, fully formed galaxies in the infant universe, objects that, by standard models, shouldn't have had time to assemble without extra gravitational help. If dark matter was denser or more potent in the early cosmos, its enhanced gravity might have turbocharged galaxy formation, squeezing gas into stars at breakneck speeds. Later, as dark matter's properties evolved, so too would its role in galactic growth. It's like baking a cake at different oven temperatures. The same ingredients yield wildly different results. The boldest versions of this idea flirt with dark matter's quantum nature. Some theories suggest dark matter particles could undergo phase transitions over cosmic timescales, altering how they clump or interact. Think of water freezing into ice, a sudden shift in state that changes its behavior entirely. If dark matter experienced similar transitions, it might explain why galaxy clusters from different eras exhibit uneven distributions of mass, or why some dwarf galaxies seem to lose their dark matter over time. Critics argue this all sounds suspiciously convenient, a cosmic fudge factor to patch over gaps in our understanding. After all, why invoke evolving dark matter when tweaks to galaxy formation physics or measurement errors might suffice? Yet the anomalies pile up, from ultra-diffuse galaxies defying mass-to-light ratios to whispers of dark matter decay in X-ray signals. The cosmos keeps hinting that its invisible half is far more dynamic than our models allow. Perhaps the most tantalizing clue lies in the cosmic microwave background. If dark matter's properties shifted even slightly during the universe's first millennia, it would leave telltale imprints in this primordial light, subtle wrinkles that next-generation telescopes might soon detect. Until then, time-varying dark matter remains a provocative what-if, a reminder that the universe's greatest mysteries often lurk not in the darkness itself, but in how it changes when we're not looking. Ultra-compact dwarf galaxies are cosmic contradictions, tiny specks of starlight, no bigger than 1,000th the Milky Way size, yet packing gravitational punches that defy logic. These dwarfs aren't just dense, they're too dense, their stars whirling at speeds that suggest an unseen anchor weighing them down. The culprit, dark matter halos so massive they rival those of galaxies 10 times their size. It's as if someone crammed an entire cathedral's worth of stained glass into a thimble. The proportions don't make sense, and yet there they are, scattered across the cosmos like celestial Russian nesting dolls. The leading theory traces these dwarfs back to a violent origin. They might be the stripped cores of once grand galaxies, their outer stars and gas torn away by gravitational encounters. Picture a peach pit left behind after the fruit's been devoured. Only in this case, the pit is laced with dark matter, its gravitational grip surviving long after the visible galaxy was shredded. Collisions between galaxies are messy affairs, and when a smaller galaxy strays too close to a Goliath like the Milky Way or Andromeda, tidal forces can peel away its outer layers, leaving behind just the dense nucleus and its dark matter halo. Simulations show these remnants should orbit their captors for billions of years, their compact starlight hiding a disproportionate shadow of invisible mass. But here's where the mystery deepens. Some ultra-compact dwarfs, like M60 UCD1 in the Virgo cluster, contain so much dark matter that their halos make up nearly 90% of their total mass, a ratio that dwarfs even the Milky Way. Even stranger, a few of these dwarfs, like NGC 4546 UCD1, host supermassive black holes at their centers, further hinting at a glamorous past. Normal dwarf galaxies don't have black holes this massive. They're hallmarks of galaxies far larger. It's like finding a tiny cottage with a vault door fit for a bank, evidence that the humble structure was once something grander. Not all ultra-compact dwarfs play by these rules, though. A fraction appear almost devoid of dark matter entirely, their motions explained by visible stars alone. This split personality, some dwarfs drowning in dark matter, others seemingly free of it, has astronomers scrambling for explanations. Could the dark matter-rich dwarfs be the stripped nuclei of ancient galaxies, while the others are simply star clusters born dense from the start? Or does dark matter behave differently in these extreme environments, clumping unpredictably like flour in an unevenly mixed batter? The implications stretch beyond these enigmatic dwarfs. If they are galactic remnants, they could be fossils of the universe's most violent mergers, offering snapshots of how galaxies grow by devouring their neighbors. Their dark matter content might even hold clues to the particle's true nature, whether it's sticky enough to survive such violent stripping or prone to scattering like sand in a storm. Every new ultra-compact dwarf discovered peels back another layer, revealing that even the smallest galaxies can carry the weight of the universe's biggest secrets. What makes these cosmic crumbs so fascinating isn't just their odd proportions, it's what they represent. A universe where darkness doesn't just lurk in the voids between stars, but coils tightly around the tiniest islands of light, whispering of histories lost to time. In their silence, ultra-compact dwarfs ask us to reconsider what it means to be a galaxy and whether size alone dictates destiny. The cosmic microwave background isn't just a snapshot of the universe's infancy. It's a palimpsest layered with hidden clues about dark matter's role in shaping reality. Among its subtle fluctuations, one anomaly stands out like a cosmic bruise, the so-called cold spot, a region of the sky where temperatures dip unexpectedly, as if something invisible had drained the energy from that patch of spacetime. This isn't just statistical noise. It's a ghostly fingerprint, one that might trace back to dark matter's most dramatic interactions, or even the remnants of primordial cosmic textures, exotic defects in the fabric of reality itself. Imagine the CMB as the afterglow of the Big Bang, a nearly uniform wash of microwave radiation bathing the cosmos. Tiny variations in temperature, mere millionths of a degree, reveal the seeds of future galaxies. But the cold spot is different. Spanning nearly 1 billion light-years, it's too large and too cold to fit comfortably within standard cosmology. One explanation whispers of dark matter's handiwork. If certain particles decayed or annihilated in the early universe, they might have injected energy unevenly, leaving behind pockets of cooler plasma. It's like watching steam rise from a cup of coffee, only to notice one patch stubbornly refusing to warm, a hint that something beneath the surface is altering the rules. Then there's the wilder possibility, cosmic textures. These hypothetical structures would be knots in spacetime itself, formed during symmetry breaking phase transitions in the universe's first moments. Picture a frozen lake cracking as temperatures drop, except here, the cracks are defects in the quantum fields underlying reality. If such a texture collapsed within our observable universe, it could have warped spacetime locally, stretching light from the CMB into cooler wavelengths and leaving behind the cold spot as a shadow. Dark matter might have played accomplice here too, its gravitational pull guiding where and how these textures unraveled. Yet skepticism lingers. The cold spot could just as easily be a statistical fluke, an improbable ripple in an otherwise smooth pond. To test these theories, astronomers have turned to galaxy surveys, mapping the distribution of matter near the cold spot. If dark matter's influence were responsible, we'd expect to see correlated voids or peculiar galaxy motions in the region. Initial observations tease exactly that, a puzzling underdensity of galaxies, as if the spot were a cosmic sinkhole draining matter away. But the data isn't conclusive, and alternative explanations abound, from foreground gas clouds absorbing CMB photons to the mere chance alignment of smaller cold patches. What makes this mystery so gripping isn't just the anomalies, it's what they reveal about our methods. The cold spot forces us to interrogate the limits of our models. Is it a flaw in our understanding of dark matter, a signpost of exotic physics, or just the universe rolling cosmic dice? Every new observation, from precision CMB measurements to deep field galaxy catalogs, tightens the noose around potential answers. Meanwhile, theorists weave ever more elaborate tapestries, exploring whether dark matter's quirks could imprint not just on the CMB's temperature, but its polarization, a subtler, richer layer of the cosmic signal waiting to be decoded. The cold spot isn't an outlier to be dismissed, it's a question written across the sky. Whether it points to dark matter's decay, space-time's scars, or mere chance, it reminds us that the universe's first light still holds secrets, and that darkness in its silence may yet speak volumes. Dark matter halos may be the universe's silent architects today, but their fate hinges on forces even grander than gravity itself. In a cosmos hurtling toward heat death where entropy erases all structure, these halos could face a slow, inevitable dissolution. Imagine a sandcastle at low tide. Even the sturdiest towers crumble as the rising water weakens their foundations. For dark matter, that water is the relentless expansion of space. In a future so distant that stars have burned out and galaxies faded to black, halos might stretch and thin until their particles drift too far apart to ever reunite, their gravitational bonds severed by the universe's own acceleration. But the story could take a darker turn. If dark energy, the force driving cosmic expansion, intensifies over time, it might trigger the Big Rip. In this scenario, not even Halo's immense gravity would withstand the violence of spacetime itself tearing apart. First, galaxy clusters would be ripped from each other, then individual galaxies, until finally, in the last frantic moments, dark matter particles would be shredded from their halos like tissue paper in a hurricane. The halos wouldn't just fade, they'd be annihilated, their existence erased in a crescendo of spacetime's self-destruction. Yet some theories offer a glimmer of rebirth. Cyclic universe models suggest that dark matter might survive each big crunch, collapsing with the rest of reality into a singularity, only to re-emerge in a new cosmic dawn. Picture a phoenix made of shadow. The same particles that anchored galaxies in one cycle could form the scaffolding for the next. Even more intriguing, certain string theory variants propose that dark matter interacts with higher dimensions, slipping out of our universe during contractions and returning when expansion resumes, an eternal dance across the fabric of existence. Then there's the wild card, quantum decay. If dark matter particles aren't perfectly stable, they might spontaneously transform over eons into lighter particles or even pure energy. Halos wouldn't collapse or evaporate, they'd quietly unravel, like a tapestry whose threads turn to mist one by one. Some models suggest this decay could fuel bizarre late-universe phenomena, like the formation of dark stars, composed entirely of exotic particles, or even trigger secondary bursts of star formation in a cosmos otherwise doomed to darkness. The ultimate irony, dark matter's fate might mirror our own understanding of it, uncertain, evolving, and bound to forces we've only begun to name. Whether halos vanish into the void, collapse into oblivion, or cycle eternally, their endings will write the final chapter of the universe's hidden history, a story told not in light but in the silent, shapeless dark. From the eerie absence of dwarf galaxies predicted by dark matter simulations to the warped halos bending light around cosmic voids, these 25 mysteries aren't just puzzles, they're windows into a hidden universe. Every anomaly, from the Milky Way's lopsided halo to the ghostly whispers of gamma rays at Andromeda's edge, reveals how little we grasp about the invisible force sculpting reality. Why do some galaxies spin too fast while others, like Triangulum, seem almost untethered? How can a galaxy like Dragonfly 44 be 99.99% dark matter, yet float like a wisp of smoke? And what cosmic drama left the bullet cluster's dark matter sailing smoothly through a collision while visible matter blazed behind it? Each question peels back another layer, exposing dark matter not as a monolithic shadow but a dynamic, enigmatic player, one that might decay, interact with itself, or even reshape its properties over eons. Future telescopes are poised to rewrite this story. The Vera Rubin Observatory will scan the skies for dwarf galaxies we've missed, testing whether warm dark matter or tidal stripping solves the missing satellite problem. LISA, the gravitational wave detector, could catch whispers of primordial black holes colliding, a smoking gun for one of dark matter's wildest candidates. And deep underground, experiments like LUX Zeppelin hunt for particles that might finally bridge the visible and invisible worlds, the most thrilling possibility. Dark matter might not be one mystery but 25 or more. Perhaps its true nature lies in the gaps between these riddles, in the way it bends galaxies while evading detection, or how it anchors the cosmos yet feels no friction. Every contradiction is a clue pushing us toward a deeper truth. The universe's greatest structures weren't built by the stars we see, but by the darkness we don't. So tell us which of these mysteries pulls at your curiosity. Is it the phantom wake's trailing galaxies, the cold spot etched into the CMB, or the enigma of ultra-diffuse galaxies clinging to existence? Drop your thoughts below and let's keep unraveling the cosmos' best-kept secret together. The next breakthrough might start with you.